Hello everyone, this is session 8 of fluid mechanics and application, and today we are going to discuss about method of approximations. So, like why we need method of approximation. So, as you know that whatever Navier-Stokes equation you write, so if you write, suppose I'm writing in vector form. Just a minute. So if you write Navier-Stokes equation in vector form minus grad p plus mu grad square v. So this is the Navier-Stokes equation in vector form. Now here, if you see, this term is the unstudied term. This is the temporal term, sorry, convective term. This is your pressure gradient. This is your viscous term. Now, also there is one some g term into k cap. Depend on what is the k. So if I take x and y, the gravity is in the that direction. So it will be g into j cap. So if that is there or not, sometimes it is under the pressure also. So we can think of as extra term, this gravity term. Now, what happens is because of this non-linearity, what is the meaning of non-linearity? So suppose here the velocity is unknown. So here what happens is if you see, if I take this term as u del u by del x plus v del u by del y plus w del u by del y. So this term u is multiplied with its derivative. So all the u is unknown, and also that we are multiplying its the derivative with respect to its value. So here both terms are unknown. So this is the non-linear term, and because of the non-linear term, this equation, Navier-Stokes equation is analytically cannot be solved. But we had seen some of the exact solutions. So in the exact solutions, what happened? We approximate that del u by del x is equal to 0. Or flow in a pipe, we approximate that the flow is fully developed. So this term is 0, like in fully developed case, fully developed case. This term is 0. Therefore, the non-linearity will go out, and it will be a simple linear equation. A simple linear equation in velocity. So that can be solved easily. But in real life, this term, this is like this thing, not always the flow is so simple or in a very simple geometry. So there is one more method that we called as a method of approximation or order of magnitude analysis. So what happens is, so first one thing also I want to say to you, if you see the Navier-Stokes equation, so first of all, there are two questions, whether it is non-linear or linear that we discussed, and which component is giving its this term, which component saying it is linear or non-linear. Okay. Second thing is, what is the order of derivative? Just like it is the first order or second order, and which component gives this? This is some basic things, so you need to understand. Now, yes. Now, how many boundary conditions required? How many boundary conditions required? So, suppose there is a method by which you can solve the Navier-Stokes equation, whether analytically or computation or any method of whatever you say. How you will solve? So, first of all, whether it is linear or non-linear, for that answer, you know that the convective term. the convective term defines the linearity and the non-linearity. Okay, because here the things that is unknown is multiplied by itself. Second thing is what is the order of derivative or so here if you see what is the maximum order that is present. Although this term is giving us the non-linearity part, but this term is defining it is a second order magnitude. Second order derivative. Second order derivative. So that means if something is second, so what terms? Viscous terms is the order of derivative and it is 2. Now, how many boundary conditions is required? So, in boundary condition, if you solve in the velocity field, because of second order derivative, we require 2 in space. Space means x, y, and z, or whatever we say. If it is in x, we require 2 in x, it is y, 2 in y. So if we say that because of second order derivative of this term, we require 2 in space and we have a time term, so we require 1 in time. So this is the amount of boundary condition that is required to solve the Navier-Stokes equation. That is 2 in space and 1 in time. Okay. So we have 2 in space and 1 in time. Okay. So this is the basic of Navier-Stokes equations. So after that we will proceed. So what is the method of approximation? So method of approximation. So if I write the equation del v by del t plus this is v vector del dot v into v vector is equal to minus grad v plus mu grad square v. So this is your Navier-Stokes equation. Now suppose this term is of magnitude 100. This term is magnitude of suppose 10. This term is magnitude of 100. This term is magnitude of 100. Now, if you see here, we say order of magnitude. Now, if you see this term is 100, this term is 100, this term is 100. Now, or I would say like make it 90. Then you will find that okay, this term is one order less, or com compared to this term and this term, and also the unstudied term, this term is less significant. So we can say that this is less significant and we can drop this term. Drop this term. So if we say we drop this term, the equation will look like this. Del v by del t is equal to minus grad p plus mu of grad square v. So you can simply see that it is a non-linear linear one w- first order two variable two variable differential equation. Now you can see that the non-linearity can be went out and you can solve these equations by like any methods. And here this term is went away. Now what happens if this whole term is went away? So if you see, if we this see that this whole term is went away, then what happens is these two terms will give a one-dimensional. So suppose I am saying that these two terms, or I will write del b by del t plus gradient of v is equal to minus grad of v plus mu of. Now, if I say that this is order of magnitude of 10, this is 100 and 100. Now we can drop this whole term and we can say that this term is of no importance compared to, it is a relative term, that this term is no important compared to this term. So if we can drop this term, it is like gradient of v is equal to mu gradient of v. So here simply you can say that it is now uh, second order ordinary differential equation. So now you can easily solve this equation. Now, what is happening? We are dropping off the term which is of less important to us. And in this way, we will find that okay, the although Navier-Stokes equation is non-linear and it is a two-dimensional in two-dimensional, it has time and space derivatives. We can reduce of the order of magnitude to some extent so that we can say, okay, now we can solve the equation. So for that, we require a non-dimensionalizing the Navier-Stokes equation. Now, what is the meaning of this? So suppose the equation is del v by del t plus v dot divergence is equal to minus grad t plus mu grad square. So we will write in x, y, and z. So first, let us suppose we are writing in x. Here, del u by del t plus u del u by del x plus v del u by del y plus w del u by del z is equal to minus dp by dx plus mu del 2u by del x square plus del 2u by del y square plus del 2u by del z square. I am assuming for two-dimensional flows, we will take off the z term so that we can just easily show how to do the non-dimensionalization. Minus del p by del x plus mu del 2u by del x square plus del 2u by del y square. Now suppose this is flowing in a over a body of diameter d with a velocity v naught, pressure p naught. Now what we will do is we will introduce a variable that is called non-dimensional variable. It is u bar is equal to u by v0. V bar similarly u by v0. Uh, Also x bar is equal to x by d. Y bar is equal to y by d. Now here we have time, so we are taking time as time t bar is equal to t by tau, and then in the pressure we can write as p bar is equal to p by p naught. Now if we do the non-dimensional term, this term, the first term, del u by del t will be v0, or I should write it here in this way, v0 del u bar by del t bar, and this term will come like tau. Now this is the first term. The second term will be this term. Now if you say this term, it is v0 square del u bar by del x bar, and x is coming with d, so this is coming at d. Now similarly with this term also the same thing will appear, v0 square del v bar by del y bar by d. Now the next term, this term if you see, if it is if we substitute on, it is only a matter of substitution, it is none other than that. So if we substitute, it is del p bar by del x bar into p0 by, sorry, I should write more clearly, del p bar by del x bar into p0 by d. Now this term, if you write, it will be del u by del x. So del u by del x is v0 del u bar by del x bar by d, and again it is coming as a derivative with respect to x, so it will be d square. Okay, so in this way, this term also will go v0 by d square del to u by bar del y bar square. Now each term is non-dimensionalized, so we can write as V0 by tau del U bar by del T bar plus V0 square by D del U bar by del X bar plus V0 square by D del V bar by del Y bar is equal to minus P0 by D del P bar by del X bar plus V0 by D square del 2U bar by del X square plus, and this term will be common. And here every term, like here if you see it has mu, so we will take this mu, and I think yeah, here we have also rho, so this rho will be here. I think I missed the rho in every term. Yeah, here also it is rho, so this term will also have rho. Okay, now this term is multiplied with rho, and this is del u bar by del y bar square, and here we have mu. So simply if we divide by rho, so and take out every term, so here it is d square, so we will send 1d here. Okay, so it is v0 d by tau del u bar by del t bar. Now v0 d by tau, this term will have rho will be gone at that side. It is u bar and v bar. So it has u bar and v bar. So it is v0. Now here I should say is t square. So this term is minus p0 by okay, so I should say we should divide it also with v0. So it is v0 here, and thus the convective term will have no other parameters. So it is v0 by dt is divided. So it is u bar del u bar by del x bar plus v bar del v bar by del y bar. This term is the extra term. Now here if you go, uh, here we have V0 will come at the V0 square will come at the bottom. So rho V0 square del P bar by del X bar, because rho is coming from here and V0 square is coming from here, plus mu by rho V0 into D del 2 U by del X square bar plus del 2 U bar by del Y square bar. So if you see, this is in terms of a U component. So similarly for V component also that can be there. So we will write it in a we will write in what you say in a vector quantity d by v0 tau del v bar by del t, and this is all is non-dimensional plus v non-dimensional dot v into this is together into vector is equal to minus p0 by rho v0 square gradient of p star plus mu 0 by sorry mu by r rho v0 d curl of the velocity vector, and it is a non-dimensional term. So every term is a non-dimensional term, and we have the coefficient. So this is the coefficient of inertial term. So coefficients we will write coefficients of inertial term. It is d by v0 into tau. Coefficient of pressure term. It is p0 by rho v0 square, and coefficient of viscosity viscous term viscous term. It is mu by rho V0D. So what it means is if you look at each of the term, this term is called Stroll number. Yeah, Stroll number. This term is called Euler number, and this term is called Reynolds number. So each term has its own significance. So what you mean by this that each term has its own significance. So for each of the fluid problem, the dominating force can be a different thing. So whatever be the dominating force, you can rely on this, and you can drop the other term. So I should write in the non-dimensional Navier-Stokes equation. It is this Stoll number into del V star by del T star plus this term is uh, again a non-dimensional term with a coefficient of 1 minus 1 by I should write Euler number or 1 by Euler number, 1 by Euler number, gradient of P plus 1 by Reynolds number, gradient of E star. So in each of the terms, if you see, this term is a this term dominates. This term is defined by the Euler number coefficient. This term is defined by the Reynolds number coefficient. Okay. Now it has a coefficient of 1. Now what is the importance of all these terms? So when we say suppose there's a question. So one question is suppose your flow is high Reynolds number. Now in high Reynolds number, what happens is you just multiply with the other side, or let us consider the first case of low Reynolds number. If you say low Reynolds number, it is Re into St. I am transferring Re here. Del V bar by del T star, so it is a non-dimensional term, plus V dot gradient into V into Re is equal to minus Re by Euler gradient of T plus. Now, when I'm saying low Reynolds number, this is the coefficient of Reynolds number only. Here it is Re into Stoll number, but we don't know whether this term is how much dominating, and also we don't know what is the significance of Euler number. But this term can be easily dropped off because when we say low Reynolds number or Re very low, this term can be dropped off, and you can simply find that this is none other than a, like if you say non-dimensional, so it is gradient of P plus this gradient of V. It is linear partial differential equation. So that can be easily solved. So in this, that is the importance of each other term. So if I say rho Reynolds number, you can say this term can be dou. For high Reynolds number also that can be done. What if someone say that Euler number is not important, or when we say that it's a times unstudied, like we do in the real problem, right, life problem, we are not given that okay, this is a steady state problem, this is a non-steady state problem. We need to decide whether that is a steady state or non-steady state problem. So going with one example, so we have a in a sea, we have a spreading of oil, and which is controlled by viscous forces, inertial forces, and particularly unstudied term of inertial forces, unstudied, and buoyancy forces. Now it says that surface tension is not important initially. Is not important initially. Now we need to find out at what time surface tension starts playing its role. Surface tension starts playing its role. So what it means is initially the viscous forces, the inertial forces, and the buoyancy forces dominates, and surface tension came into picture after some time. So the question is, when it will start playing its role? What is the time? So the thing is, we need to see so that if you write for the uh, inertial term, if you say what is the order of magnitude, it is mass into acceleration. Mass is rho into LC cube. I'm saying in terms of characteristic dimension. Into acceleration is v by tau. So if I write it is rho LC cube v by tau. Now what is the surface tension force? It is sigma into LC, some characteristic dimensions, and okay, that is it is the same. Now if I say Fi by or Fs by Fi, so it is sigma Lc by rho Lc cube into V by tau. So this will be square. It is sigma by rho Lc square V by tau. Or I should give tau at the top side. Now, when this term, that is Fs by Fi, is less than 1, that means your surface tension force is very weak in comparison of inertial term. In comparison of inertial term, then surface tension is not important. Surface tension is not important. So for this condition, if I say um, sigma by tau, uh, or I should write it as T, sigma by T by rho Lc square into V is equal to 1. So if it is very, very less than 1, so I should write it as less than 1. So what is the dimension of velocity? So velocity is Lc by Tc or T, and this volume is the order of Lc1 raised to the power 3. So we will try to uh, solve in this way. So we will replace velocity with Lc by T, and so if I say it is T square by rho Lc cube into this should be less than 1, and sigma T square by rho into volume, that whatever volume has been spilled should be less than 1, and it says that T should be less than rho S, or I should write it as rho by rho V by sigma. So for the time less than this value, we can say that surface tension force is not dominant. So I will mark as a line at this point and at this point. So this value is under root of rho V by sigma. So and this term is like less than this term, and this is greater than. Now what happens is, this is, I think I should write as T is equal to T less than it is tau. T less than tau and T greater than tau. For this side, surface tension force is not important. Surface tension force is not important. And for this side, it is significant in comparison to inertial term. So here you can see that with the order of magnitude analysis, we can say that for the what time scale, we can say that surface tension force is not important, and for what time scale it is important. So suppose a data I am giving that oil has been spilled in a sea, so sigma of oil is 0.02 Newton per meter. volume that is spilled is 100,000 tons, and that so we need to find and the row of oil you can take any 800 or something kg per meter cube, and it is said that for what time you should not consider surface tension force. So if you obtain TS, it is at approximately 20 hours. So till 20 hours, the surface tension force will not be important, and after that, the surface tension force will came into the picture. So this is the one example of how to like what is the importance of each other term and how to solve. Now the second question is we have a very so this is the size of B, and this bottom plate, both are the plates. So this is the plate, and this bottom plate has been oscillated with V0 sine omega t. Okay, this is your y direction and this is your x direction. Now it says that uh, till till what time your inertial force is important and till what time the viscous forces are important. So first of all, because there is no any variation of this velocity in x direction, we can neglect the convective term because here del u by del x is equal to 0 and only u component is present, v component is 0. That is why the convective term will go off. The convective term will be 0. Therefore, the inertial term is there and the pressure term is there and viscous term is there. Now we are saying that this B is not as large as we want and there is no any gradient. The flow that is happening is because of this oscillation, not because of pressure gradient. So pressure gradient will also not come into picture. So only two forces are inertial and viscous forces. So I last time I told you how to write inertial forces in order of magnitude. Inertial forces is rho, or I should write mass into acceleration, or rho LC cube into acceleration is v by tau or v by t. So that is rho LC cube into v is v0 because the highest magnitude can be v. So I should write it as here. LC is equal to b because this is the characteristic dimension. V is equal to v0 and t is equal to 1 by omega. So this is the order of like B is order of magnitude of B, V is order of magnitude of V0, and T is 1 by omega. Therefore, inertial forces is equal to, if you say rho B cube, V is V0 into omega. Okay. Uh, Now, what is the viscous forces? So, viscous force is mu du by dy. This is the viscous force. So it would be mu v by whatever the characteristic length b. So this is v0 by b. And so therefore viscous force is order of magnitude of mu v0 by b. Hence, if I write it inertial by viscous, the ratio it would be rho b cube v0 omega by mu v0 by b. So du by dy, and here it is this v0 will be go out and uh, okay, so it is actually If you see here, it is written as rho Vd by mu, so it is like that only. Viscous forces is the importance is as mu into V0 into d by mu. Sorry. It is okay. Now, if I write it as in this way, or should be mu V0 by b only. Okay, let it be. So, this is the this is the denominator term. So, if you take ratio rho b raised to the power 4 by mu into omega. So, what it means is if you say yes, everything is I think you are right. Okay. So, if I say my inertial to viscous is much less than 1, um, or I should write it other way. Yes, it is much less than 1. That means your inertial is much less than viscous. So inertial term can be dropped off, and if you write it is rho b based upon 4 by omega by mu is much less than 1. So omega is much less than mu by rho b raised to the power 4. So that means if I'm saying it is omega is equal to mu by rho b raised to the power 4, till here we can drop off the inertial term, and the flow can be assumed to be a steady state or quasi steady state uh, velocity profile. But although you are saying that here your velocity is v0 sine omega t, so how it is happening? So that means velocity is not varying with time. So it is like that at the bottom of the plate, suppose it is oscillating in this way, and this is the top plate, so here velocity is 0. So for any location with the plate, the fluid layer is oscillating here and there, but in this way. So here it is, if you see this with the oscillation, this layer is oscillating and going here and to fro, and the velocity profile is, and also you can see from the other term because the initial term has been dropped out, this is equal to 0, and velocity is a linear velocity profile. That means with y the velocity is linear for any instant, and it is going in this way, and like it is to and fro motion, and it's for any location it is a linear velocity profile. So that is what is the meaning of dropping of the term and mu. Now suppose here if you see, if I say here that this term I should write in another way. This is like in this term, what happens is your inertial is significant compared to viscous. Then what happens is you say that it is del V by del T is equal to 0 because inertial can be like viscous can be dropped off. Viscous is equal to 0. Suppose it is there. Now what happens is V is equal to some C into T. But you know that we have two boundary condition at this point. One boundary condition is no penetration boundary condition. Second is a no slip boundary condition. So dropping of a viscous term will lead to a error of what you say. So when you say that it is a, if you apply any one of the boundary condition, the second boundary condition would be violated. Then there may be a problem. So what is the solution of that? So the solution is um, our from the basic assumption we assume. So our assumption is wrong here. So for the second condition, so here it is said this is B and it is X and Y and it is oscillated with V0 sine omega t. Now, what is happening? What happens at that time? At the when mu is greater than this. So here, the our basic assumption is that the characteristic length is the whole dimension of the B. But suppose if that oscillation is propagating only a small depth, not propagating at the other depth, at that point the viscous term is zero. But here the viscous term is significant. So, so what we will do is we will like inertial term and that term will change. So inertial term will become it is mass into acceleration. So mass into acceleration it is rho LC cube into V by T. So rho into LC cube is LC is will be there. It is not equal to B into V0 by in V0 into omega. Now viscous term, if you say viscous term is um, so it is okay. Yeah, I had done one mistake. So here it is viscous term is um, into area of cross section. So it will be L square. So I should write in otherwise it's error. Mu V by LC into LC square. So it is mu V into LC or it is also equal to mu V0 into uh, B. So if you write mu V0 into B, 1B will be what and it will be B square into B square. Okay. So here it will be B square and this will be B square. Okay. Yeah, everything will be same now. So here also it is into area. So it is mu V0 by LC into LC square. So it is mu V0 into L. Now what is this LC? Over this viscous force is dominant. So if you take rho LC cube V0 into omega is order of mu V0 into L. So V0 will go out and this LC cube is LC is the order of magnitude of nu into nu by omega under root. So yeah, so that means for any particular omega, this is the LC where this term is uh, or I should say for any particular omega, this is the characteristic length. So for particular omega, this is much length is what the field, what is the viscous forces are there. So till here the viscous forces are present, and after that the velocity, the this layer is stagnant or stationary. So that is the meaning of what is called as. So this is what is called as the boundary layer. So here the disturbance is felt only in this location. Disturbance is felt only at this location, and here no disturbance. Okay, so this is in this way you will like solve the problem, and this is the length where you can say that where the forces are where the forces are very significant. Now the another problem is what is called as row low Reynolds number flow. It is also called Stokes flow, and it is also called as creeping flows. So what happens is this is your event. Yes. So this is your equation. Sorry, I should copy this equation. Yes. So now in Stokesian flow, what it says it's a uh, low Reynolds number. So here the Reynolds number is much less than one. Suppose it is like in this way. Now each term, so this is Stall number into this non-dimensional term plus is equal to I should write as minus 1 by Euler number into gradient of P star plus 1 by Re this star. Now what happens is if you multiply at both the sides and it is saying that it's a road and all number flow. So the thing is we can drop off this term, the inertial term, and we can say that Re by Euler gradient of P is equal to this viscous term. So here the pressure term is significant to viscous term. And this is what is called as Stokes flow, Stokesian flow or Stokes flow. And this is for the low Reynolds number flow. So what it means is, so if you say suppose you have a system or a sphere and the flow is happening, so it says that at this point we have a stagnation, and at this point you have a very like a flow over in this way over a body. Okay, so this is the streamline for the flow, and at this point we have a zero velocity, and at this point we have a v0 as a velocity. So velocity will vary as in this way at this point. So this is what is called low Reynolds number, and we can simplify by initial term can be neglected, and we can use this term, and or I should write as initial term neglected because it's a low Reynolds number and steady state problem. Okay, so this in this way you will solve this equation. Now, the the second thing is for high Reynolds number, the, the only term that can be dropped off is a viscous term. So again, viscous term can be neglected. But the problem lies with dropping the viscous term as the order of magnitude will be changed. So whenever there is a problem where dropping of a term lead to uh, changing of the order of derivative, that leads to a problem of employing the boundary condition. So suppose this is happening and you have a plate and a very high Reynolds number, the flow is happening. So if you drop off the viscous term, the thing that will happen is you cannot apply in the space direction. So what is called as, so here we have what you say, no slip boundary condition, and you have or you say tangential velocity is equal, sorry, normal velocity is equal to zero. So you cannot apply both the things simultaneously. So what happens is, so suppose this is your flow over a sphere and the flow is happening. If we apply this higher Reynolds number, this what we say assumption, the thing that will happen is at this point you had don't will your solution will not follow the solution will not follow no slip boundary condition. That's why we will not assume. So the thing is I need to put we will not drop that term which lead to what you say which lead to change in order of derivative. Otherwise, the boundary condition would not be satisfied. So the next problem is it's a terminal velocity problem. So okay, so also one thing in this one thing in a roll and all number flow or Stokes flow, we said that Reynolds number into stall number del V by del T is equal to minus Reynolds number by Euler number plus uh, viscous term. Okay. Now this term is none other than what you say. If you multiply this term with this term, you will get what is called as Re into stall number is the order of magnitude of d square by nu into Tc, some Tc. And so this has a coefficient of 1. So coefficient of inertial by viscous is equal to d square by nu Tc. When this coefficient, so I'm saying when inertial divided by viscous is much less than 1, then we can say that we can drop inertial in comparison to viscous. And what is the time scale? So d square by nu Tc should be much less than 1, or T should be much greater than d square by nu. So for this time, so if I'm saying suppose this is the time scale and this is tau is equal to d square by nu, at this point you can say that your is inertial term in a unsteady state inertial term can be dropped off. So it is less significant. And at this point you have inertial term is significant. So that means if my time in order when we are studying or analyzing the problem, if my time scale is this much, or we say when this is very less, we can drop off this inertial term and we can solve as a simple this equation. So in this type, uh, we can drop off the inertial term and it is only a this pressure gradient term and a viscous term will only be there. So what that is what the importance of like order of magnitude, and you can say that for the time scale, we can say that if time is much greater than or time greater than, or I should write is as only a less than. So after t greater than d square by nu, you can say that your inertial term is less significant. So the same thing happens. So you have a terminal velocity. So terminal velocity, what it says is, so in terminal velocity, suppose we have a large tank filled with a viscous fluid, okay, filled with a very viscous fluid, and you drop a ball at the top. Now what happens is when you drop a ball, it will be go on because the velocity will increase, because initially it is a zero velocity, then velocity will increase. So with as suppose this is the z direction, when z increases, velocity increase, that means your drag will increase. Okay. Now uh, with z increases, so if you say the drag will increase, and therefore we have a mg here that is event that is actually happening, and this is the drag force. So with time at at some z and t, what happens is this mg, or I should write as weight is approximately equal to drag. Okay, or and one force is also at 2.4, but I should write apparent weight. When apparent weight is equal to the drag force, the velocity will be constant because at that time these both are equal, so the velocity would be constant, and this velocity is called the terminal velocity. Terminal velocity. So we will try to find out what is the time scale over which we can say that the terminal velocity is achieved or not, because this time scale will say that whether these forces are balanced or not, or we can neglect the unsteady state. So this is the term R into stall number is equal to minus grad of P plus mu of grad of V plus some buoyancy force or the weight term. So it is rho minus rho of sphere minus rho of liquid into what would be there? This is density. So okay, I should write as a buoyancy term plus buoyancy term. Now, at what time this unsteady particles will be there or not? So we will write as inertial force. Inertial force is rho s d square by mu into t, and your viscous force is order of magnitude of rho v into what is say d. Uh, I should see what I have written. Or it is mu vl, sorry, mu v. It is mu into whatever the velocity into L, or I should say d, because d is a characteristic length. And this velocity can be written as some characteristic dimension d by divided by t. So, or uh, let me see, it is rho Vc as your what you say dc dc cube divided by t. So this is what is called the acceleration, and here we can also write as mu vd, mu vc into dc. So if I take the ratio, this ratio will go out as rho vc dc cube by t into mu vc into dc. So vc will go away and this dc will be dc square. So you will get rho dc square divided by mu into ts. Now, when you can say that terminal velocity is achieved, when inertial term, unsteady state inertial term is much less than viscous term. Therefore, this term rho dc square by mu ts is less than 1, or when ts is greater than rho s d square by mu. So for at this time, we can say that you can neglect unsteady state term can be neglected. So suppose you have a steel ball of diameter 0.1 mm, and rho s is equal to 7480. That is means steel density 80 kg per meter cube. So at what time the terminal velocity is achieved in the order of magnitude, and whether that case is whether terminal velocity will achieved or not. So you can solve with putting this value, and you will get Ts is equal to 0.0 in a water. So rho mu of water you can take 0.01 Pascal second. It is 0.028 seconds. So After this time, we can say that the unsteady term can be neglected, and the thing is now the terminal velocity is achieved. So this is the meaning of this term. So now after 5 minutes, we will try to look into the problem more. So till here, we will discuss about some other things. Then we will go some with some new problem and try to solve it. Try to solve that. After 5 minutes, we will meet. Now we will try to analyze about what is called as boundary layer problem over a flat plate. Boundary layer problem over a flat plate. Okay. So, suppose you have a flat plate, um, and you have a velocity here, v0, and the flow is happening. Okay, the flow is happening. Now, the thing is, when a flow is happening, what is the order of magnitude? This term can be dropped off, this term can be retained. So that thing is, the thing is, so we all know that boundary layer is formed in this way, like at this point, and it will go on increasing. So how we will see that whether which term is significant and which term is not? So, um, if you write the Navier-Stokes equation, it is W by del T. So it is X, it is Y plus, and this length is L, total length is L, plus U W by del X plus P W by del Y. This is whole is multiplied by rho is equal to minus del P by del X plus mu del 2U by del X square plus del 2U by del Y square. This is a two-dimensional flow. Here also it is del V by del T plus U del V by del X plus V del V by del Y is equal to minus dP by dy plus mu del X square plus del UV by del Y square. Now the thing is, it will be what you say, a steady state problem. This temperature term will not be there, but which other term will be there, which other term will not be there, we will to find out. So now we will say non-dimensionally u is, or we should write each of the term. So I should make a little space for each other term. So this term will go here, and we have a continuity equation for an incompressible flow. It is del v by del x plus del v by del y is equal to 0. Now, what we will do is we will try to like see which term is significant or not. So first of all, if you say this term, um, this term will be, if I say u, so u can be anything v0 divided by L length is order of magnitude of same equal to vc. So for u we know it is in x direction, so v0 is a characteristic dimension. But for v we don't know which what is the velocity, characteristic velocity, and this y we don't know. So it is some length of delta. So vc is v0 into delta by L. Okay, this is the term. Now, if we write each of the terms separately, so here it is this term, it is v0 square by L. If you write this term, it is vc into v0 divided by delta. And if you substitute vc from this term, it would be v0 square by L. So both term has a dimension of v0 square by L. Now this term we will see next time. Here if you go mu times, so I think rho would be here, rho would be here. Okay. This term is mu times this first term is mu times v0 divided by L square, and this term is mu 0 v0 by delta square. Now that the assumption that delta is much less than L, this is the assumption, and from there we can say that uh, this term can be dropped off to equal to 0 compared to this term. Now, if you say in this term already is equal to 0 because of the unsteady part. This term is V0 into VC divided by L. And if you say it is substitute V0 is V0 square delta by L. Similarly, the other term is also V0 square delta by L. This is minus del P by del Y. And here also you will say VC by L square and VC by delta square. So this term will equal to 0 because delta is very, very less. And VC is V0 delta by L. So it is V0 delta, or I should write delta by L by delta square, so it is by L into delta. Now, if you divide each of the term, like if you say x momentum and y momentum, so if you take two ratios, so this is all row. If you take this ratio, you will find out that inertial x by y is order of magnitude of uh, it is L by delta. What it means is, or I should add in other way, then you will get a very good understanding of. If I say y by x inertial, it is order of magnitude of delta by L. That means, and we know that delta is very, very less than L. Therefore, we can say that the each of the term, because in each of the term, y momentum is one order less than x momentum. So each of the term is not significant as compared to x term. Therefore, this pressure term is also one order less significant than the pressure term in x direction. Therefore, this term can be dropped off, and we can say that here this partial derivative will change to ordinary derivative, that is dp by dx. Okay, this is the first assumption. That means the pressure variation will not happen in y but in x. So in y, you don't have a pressure variation. So what is the what you what is the merit or the good point of this? Let's suppose, so boundary layer, till boundary layer, you have a viscous that is felt. After that, there is no any viscosity that is felt at this point. So whatever be the pressure condition at this point can be directly imposed on this plate. Because the pressure is not varying with y. Now, if I say that my inertial term and the viscous term are significant and both are of same magnitude, so inertial term is same magnitude of viscous term. That means rho V0 square by L is the order of same order of magnitude as mu V0 by delta square. Now, slightly substitution if you make, you will get delta square by L square is mu L, sorry, L would be not here, it is at the bottom. That is mu by rho V0 into L. So, or delta by L is 1 by RE under root. That means if you say delta by L is 1 by RE, that means initially we assumed that the initial assumption was initial assumption was delta by L is much much less than 1. That means this can be only possible when RE is much much greater than 1. Therefore, the this assumption that delta by L is under root of 1 by RE is only valid. This is called the boundary layer analysis of a flow over a flat plate. Flat plate. This can only be valid when Reynolds number is much much greater than 1, or it is called a high Reynolds number flow. And the thing that is within the boundary layer, there is a pressure distribution in the x direction but not in y direction. So this region is called a inviscid region. Inviscid region means here the viscous forces are not that important. That is called the inviscid region. So whatever pressure gradient is existing in this direction along the x direction, so suppose dp by dx is existing in this direction, you directly superimpose in this superimpose and you will get that this del P by del X term. So in the inviscid region, we can apply Euler equation or Bernoulli equation also. We can apply Bernoulli equation, and Bernoulli equation says Bernoulli equation says P plus half rho V square plus Gz is equal to constant. Now, if I take derivative with respect to x, it will be rho Vc dVc by dx is equal to 0. Now, you know that the velocity is not changing along the x direction because it's a flow over a flat plate, so no area is changing, therefore no velocity is changing. This term can be dropped off to 0, that therefore dp by dx is also equal to 0. That means there is no any pressure gradient in x direction. Therefore, your equation for the boundary layer will simplify to del u by del x plus v del u by del y is equal to mu del 2 u by del y square. So this is a boundary layer equation. Okay. Now, this happens over lower flat plate. Now we have another problem, another question of this same boundary layer problem. It says that, so suppose you have a question is there. You have a free convection problem, and it says mm, you have a momentum equation in this way. I will write, then it will be easy. This is your Navier-Stokes equation. Okay. So it is for the free convection, you know that this is your buoyancy term. So what is free convection? So when you have a heated plate, the because the heat, the air will induce its velocity at the top, and therefore what happens is you will get a velocity not from any external means, but because of the what you say density difference that will create the velocity. This is an inertial term, convective term. This is your viscous term. Now the question is, so and also beta is equal to minus 1 by rho by del t at constant p. Now the question is, find the condition over which this buoyancy terms is this this buoyancy term will is unimportant, and also we need to non-dimensionalize the term. So what is the condition for which this buoyancy term is not important? So first of all, we need to find what are the terms that will drive the flow, and what are the terms that will be important. So for let us non-dimensionalize this. So whatever the x bar is x by L, y bar is y by L, Vx is Vx bar is Vx by V0, some velocity, Vy bar is by V0. Now that temperature, because here we have a temperature, we will write temperature in terms of non-dimensional variable, this non-dimensional variable, and we will substitute each of the term in this equation. So if I substitute it, what you will get is V0 square Vx bar del Vx bar divided by del S bar, and here it will be L. So this is the first term, plus similarly for this also the same term will come. So I will write in bracket Vy bar del Vy bar by del Y bar is equal to G into beta into T wall minus T infinity into theta. So I am just substituting plus mu by rho 0 and here we will get V0 by what we call L square del 2 V bar x by del x bar square plus del 2 V bar y by del y bar square. So each term is non-dimensionalized, and you will see the coefficient. So I will take this coefficient on the right hand side, this coefficient, or I should make a viscous term at this term. So we will try to. So this is your convective term. This is your convective term. This is your buoyancy term. This is your viscous term coefficients. So the thing is, first thing we will do is what is called as buoyancy divided by viscous. So if you take these two ratios, G beta Tw minus T0 into theta divided by, if you say it is mu V0 by rho 0 L square. So if you say it is G beta, I am saying delta T into theta. Uh, so it is mu V0 by L square, and so mu 0, I take mu 0 square and L. So G beta delta T theta by mu V0. I should add as mu V0 into L square. Now there is term that is not here, so I should, if I take this term at the right hand side, so this is gravity term is, just a second, I will see what that is going on. So if you see, it is okay. So the only term that is here is V0. Vc by. So if I take this term at, so by V0, so mu 0 square. If I say this L0 square del Vx by del y bar mu 0 by rho, it will be okay. So if I just write in this way, let's make it in different way. So this is your right hand side. So now it is mu by rho 0 into L square will go here. So I make it L cube and multiply at the denominator as V0L. Okay. So here also mu, so it is will be mu square. So this will be mu. So this is what is called as, and here also it is rho 0 square. So if you say this is what is called as Grashof number, so this term is Grashof number, this term is Reynolds number. Okay. So this is what is called as buoyancy divided by viscous. So buoyancy divided by viscous will say that that is called the Grashof number by Reynolds number. So if your Reynolds number is very very high, that means, or this term, uh, if this term is very very high, so this is also called as the ratio is called Richardson number, and it says that it is Grashof number divided by number. So if it is very very high, sorry, if it is very very first, one condition, if Richardson number is approximately equal to 1, that means natural convection, or what you say free convection, free convection is same order of magnitude as forced convection. Okay. Now, when this number is greater than 1, that means your GR is greater than RE, and that means free convection is greater than forced convection. And when it is Richardson number is less than 1, you can say that GR is less than RE and the free convection is less than forced convection. So this Richardson number is the criteria where we can say that whether what you say that term is important or not. So that can be like significantly addressed um, with this whether that is there or not. Okay, so like this is how you uh, this is how you solve like whether that is important or not. And the second problem for this same question is we have given um, we have given a condition that if your air flows at 300 K, so temperature is given at 300 K, past the 3 centimeter, that L is 3 centimeter long plate, and TW wall is temperature is 100 degrees Celsius at 10 meter per second, are the buoyancy term negligible? So for this term, you need to find what is the Grashof number, that is d beta delta T L cube. So one thing also I think is there. Um, okay, so this is V0 by L square. So G beta delta T L cube by mu square, and you will find Reynolds number, and then it is rho V D by mu or L by mu, and just check whether GR by RE is less than 1 or GR by RE is greater than 1. So if it is less than 1, then we can say that your free convection is neglected, and if your GR is greater than 1, you can say that free convection is significant. Free convection is significant. Okay, in this way you can solve this problem. Now the second case, it has the problem. It is said that when there is no any viscous term, so suppose this viscous term is not there, and like if there is no any velocity that will induce a viscous term. So what is the induced fluid velocity? So it means that only the buoyancy force is induced, and this term is there. So you need to equate the inertial term with the buoyancy force. So I should write inertial by buoyancy, and inertial by buoyancy is order of magnitude of um, okay, so it is g beta delta t, or I should write g beta delta t, or I should write as into theta, g beta delta t theta divided by v0 square by l, v0 square by l. So now if these two are significant, that means this is it tends to be 1, and g beta delta t into theta, or t wall minus t wall minus t0 into theta is equal to v0 square by l. This both will be of same order of magnitude, and you can directly obtain the v0 as z beta delta t theta, or so the okay, so it is yes. So here it is not the theta would not be there. So z beta delta t z beta delta t by v0 square by L. So if you just equate the both the terms, you will get v0 as the order of magnitude of z beta delta t into L under root. So this is what is the induced velocity. This is what is the induced velocity at the initiation, and once that would be there. So if you say what is, if I say the question is your delta t is equal to 100 minus 3, so T0 is equal to 300 K, T wall is equal to 100 degrees Celsius, length is equal to 30 centimeter, G is equal to 9.8 meter per second square, and beta is equal to 1 by T, and this T should be in Kelvin, and it is the average film temperature, it is T wall plus T0 by 2. So if you simply put and solve, you get a V0, approximate V0 of what is this value. Okay. Now, there is yes. So this is the coefficient. So it is coefficients. I should write as coefficients. Coefficient of inertial and buoyancy force. Now, this will be helpful when you will solve the problem that whether this term is important or whether this term is not. Okay. Also, so in the boundary layer problem, we had solved this as delta by L is order under root of 1 by RE. So delta by L is 1 by under root of RE. There is what is called as shear stress, that is CF into half rho U square, and also tau is equal to mu du by dy, and that is equal to mu v by delta. So if you substitute delta here, you will get tau is order of magnitude of mu. And this is from the boundary layer only. Boundary layer. Tau mu v is what is uh, some v0 by delta is, if you say, it is L by I should write in the reverse way, under root RE by L. So or it is also equal to mu v0 under root RE is under root of rho vd or rho vl by mu into by L. So the shear stress is, if you say, yeah, so here you say it is mm, V0 by delta square. So here it is delta is yes. So it is rho VL by mu. Now it is if I say it is under root of mu would go inside. So it is mu V0 cube because square and cube, and then divide by into rho by L. So in this way you can say that the shear stress is dependent on that, and the shear stress is also equal to CF into half rho U square, that is also equal to V square. So what it means is, so we will drop the half term. Okay, the half term will go away, and CF is, if you write, it is because rho is here and here is square root of rho. So it will go at the bottom. So rho V0 rho by L into rho square into V raised to the power 4. Because it is square, so it will go here with the power 4. So if you simply substitute, this rho will go away. There this V will go away. And it will be again mu by rho LV 0. And this term is none other than again 1 by under root of RE. So you can find that your coefficient of drag is also equal to root, from the order of magnitude analysis only you can find that it is under root 1 upon under root of RE. So that is what is beneficial in terms of what is called as um, order of magnitude, that you can find whether what is the coefficient of drag, and how you can solve this. Now, another question. There is one problem. It is called Stokes' first problem. So you have very large tank and it is filled with water, and you just put a plate or that can move, and you induce a velocity. Okay, that is from V0, and it's not pulsating. So the thing is, if I just write um in terms of what you can say, the equation of image Stokes, it is del V by del T plus U del V by I should only this is your x direction, this is your y direction. So let me write in y direction only, because in x direction there is like or let us write in del u by del x plus del v by del y is equal to 0. U del u by del x plus v del v by del y is equal to mu del 2 u by del x square plus del 2 u by del y square. Again, the third term is u del v by del x plus v del v by del y is equal to mu del 2 v by del x square plus del 2 v by del y square. Now you have continuity momentum equation. So what it says is, okay, now what we need to do is, we know that from the this equation, it is this x is very large and this y is approximately, we say it will change with time. So at the bottom there is a plate. So first of all, if you say this term will be zero because there is no any velocity gradient term in x direction, and therefore this term is also equal to zero because of del v by del y is equal to zero. That means v is not a function of y. Therefore, whatever v at this point will be v at any point. So because this is a plate, there is no any velocity component in normal direction. Therefore, v is equal to zero for every other point. So this all term will go away, and this term will go away because of this del by del x equal to 0. This term will go away, and this term will go away. Therefore, what happens is, also I didn't write this term del u by del t. Now this term will also go away because v is 0. So therefore, what happens is rho del u by del t is equal to mu del 2 u by del y square. So at writing the order of magnitude, we say that this term is rho v0 by some t is this term is mu v0 by delta square, or some on what till what boundary this delta is felt. So if you solve this, you will get delta is order of magnitude of this v0 will go away under root of mu t, or what is called as kinematic viscosity into time. That means when we say with time, so if I say that this is what is called as v0, what is the start place, and this is your x. So initially, when t is very less, this delta x is also very less. Okay, till what it is direction x, till what distance it is felt. And when t goes on increasing, it will also go on increasing, and in this way it will increase. Okay, and this is the graph as t is increasing. So if I induce a new value, okay, so this is what is the order of magnitude of scaling the problem at how to solve this Stokes first problem, because the viscous layer is only this much, and only this till this layer this is felt, and after that it is not felt after and all this time. So if I say the at this point the velocity is not induced, and with time it grows, because if you see with time the x grow and the velocity is felt in more direction, more of the layers. Okay, so like let me find out some of the other problems. Okay, so the another question is, okay, so the question says it is a terminal velocity problem. Find the size of a glass particle of density 2800 kg per meter cube settling in water at a speed of 7.5 meter per second. So it is a terminal velocity problem. So if you say in you have a tank and it is filled with water and there is a glass bead, and it says that the terminal velocity that is achieved is 7.5 meter per second, and we need to find out uh, what is the size of this particle, or ultimately it is what is the diameter of this particle. If you say it is a spherical particle, it is spherical particle. What is the diameter of the particle so that it will achieve a terminal velocity of 7.8 meter per second. So if I solve this, so first of all, what is the forces that is happening in this glass bead? So if I say the forces, first is the mass of the gravity forces. Because it is going into the water, there would be a buoyancy forces, and that is buoyancy forces from the Archimedes principle is equal to rho of liquid into the whatever be the weight of the liquid that is displaced, pi by 3 r cube into g, and the drag force. So the drag force, that is Fd, is equal to 6 pi eta, or I should say 6 pi mu rv. This is the terminal velocity. This is the dynamic viscosity. This is the radius of the ball. And so, if I say the terminal velocity is achieved, that means there is no any steady state term. Therefore, the force whatever is acting, that is downward, mg, is equal to rho l 4 by 3 pi r cube into g. This is the buoyancy force plus 6 pi mu rv, or capital small r. Okay, small r. Now, this energy can be also like written by in this way into G. This is the volume into rho of glass into G. This is what is the weight is equal to rho of pi r cube into G plus 6 pi mu rv. So you can directly calculate what is the terminal velocity that is achieved, that is equal to 6 pi mu rv. So this r will go away and it is r square. So velocity that is achieved is 7.5 meter per second. So therefore, R value that you will get is 4.1 into 10 raised to the power minus 5, or approximately this is meter, or equal to 0.04 mm. So this is the size of that whatever be the droplet, and that will lead to uh, the terminal velocity of 7.5 meter per second. So the another question is what happens if I say the new terminal velocity is 4 meter per second? What happens to the size of the ball? So you can see that velocity directly proportional to r square. If you say velocity directly proportional to r square, so v1 by v2 is equal to r1 by r2 whole square. Now the initial velocity is 7.8. The now new velocity is 4 meter per second. So 7.8 by 4 is equal to r1 is 0.04 by r2 whole square. So r2 is equal to under root of 4 by 7.8 into 0.04. That means it would be less than because the velocity is reduced, so less diameter of the term will be. So if you solve this, it would be 7.8. So the diameter now is 0.0286 meter mm. So in this way, you can see that the diameter directly proportional to r square, and you can easily solve like what is important and what is not. So therefore, in terminal velocities, your inertial term are assumed to be zero, and it is there because your velocity is not changing with time. And therefore, you can say that whatever be the force that is acting will um, will be balanced by the gravity force. Also, there is one problem that so suppose if you have a cloud and you have a water droplet and it is falling with such a high altitude of suppose a very high altitude of around 1.5 kilometers. Okay, and uh, because v is equal to under root of 2gh, this is from our mechanics if we solve. So whatever velocity this will achieve, if you put the height, it is 2 into 9.8 into 1500. So the velocity that can drop that a drop can achieve is v is equal to 171.4 meter per second. So if a drop is free falling, it can achieve this much velocity, and that is very high. If you just multiply with 18 by 5, you will get in kilometer per hour. So if I just give you a sense how much high it is approximately equal to 620 kilometer per hour. But although the drop falls, but it is not, this drop is not achieved that much velocity. 620 kilometer per hour is very high velocity, but drop is not achieving that velocity. Why that is happening? So why drops falling from such a high altitude, such a high altitude, not gain such velocities, not gain such velocities. The thing is that this is not happening because the drag forces came into play, and the drag force will reduce the velocity because if you say um, your drag force, so forces I will draw. So drag force is 6 pi mu rv. That means it is linear with velocity. So if I say the velocity versus forces, you will get drag forces like this way, and the buoyancy force is it is a constant value, so it is some this value. So because it is increasing in this way, you will get a point where this buoyancy force will be balanced by this viscous force. So this is your drag force, and this is your buoyancy and a weight buoyancy, net buoyancy. Then you will get a point that is called V star, a terminal velocity, and after this, there is no any change in velocity, and this velocity is achieved. That's why Although rain is falling from such a high altitude and a drop is following, but it will not get a velocity which is assumed to be that 620 kilometer per hour, not achievable for a drop. So that is the importance of what is called a terminal velocity. Okay, now we will. Mm, I think you can solve the most of the problems. So in the assignment, so if you see the assignment, so in the assignment you will get a problem of that what I talked to you about non-dimensionalizing or normalizing. We can say normalizing Navier-Stokes equation. So normalizing Navier-Stokes equation. Again, I am repeating that this is the coefficient into del V star by del T star plus V star dot this term into V star is equal to 1 by Euler number, this pressure star plus, if I say the gravity term separately, it would be 1 by Froude number square and G gravity term, or plus 1 by Re into detent of velocity. So you can see that all these terms, so all these term has it. So if I say it is there or not, it depends. So if that is there, so if that is there, then it will be a Froude number. So each term, so this is the coefficient of inertial term, unsteady state inertial term. Here the coefficient of convective is 1. Here it is what you say 1 by Euler number and 1 by Froude number square. So this is for the gravity term. This is 1 by Re square. 1 upon Re for the viscous term. So I hope you can solve your assignment problem. Most of the things are discussed from there only. Um, and in next, we will meet in the next class. Thank you.